A spacecraft wall cracks. For a fraction of a second, nothing moves. The cabin is still. A tethered tool hangs in the air. A globe of water floats beside a panel. Red emergency light washes across the metal walls. Then the crack opens wider, and the room seems to exhale all at once. White vapor blasts outward through the gap. Loose droplets stretch, shiver, and swell into tiny bubbling spheres. A cable snaps tight. A paper-thin layer of frost flashes across the edge of the metal. The sound inside the cabin dies into a violent silence, because the air that carried sound is being ripped away. Outside the window is black space. Inside the cabin, the danger is not that space is pulling like a monster. Space is not a hand. It is not suction with teeth. The danger is simpler and stranger. The pressure is disappearing. That is the part movies often get wrong. The human body is not a balloon waiting to pop the moment it touches vacuum. Skin, tissue, and circulation have strength. They contain the body far better than the movie version suggests. A person would not instantly explode. Blood deep inside the circulatory system would not simply erupt into a cloud, but that does not make vacuum gentle. It makes it quieter. The real damage begins where pressure is supposed to be invisible. Air inside the lungs, dissolved gases in body fluids, water exposed on wet surfaces, oxygen moving from the lungs into the blood. All of these depend on surrounding pressure. Remove that pressure fast enough, and the body is still shaped like a body, but the rules inside it begin to change. The floating water droplet is the first clue. In the red cabin light, it expands. Its surface trembles. Tiny bubbles appear inside it, not because it has become hot, but because the pressure around it has dropped so low that water can behave as if it is boiling at a much lower temperature. Boiling is not only about heat, it is also about pressure. On Earth, air presses down on water. That pressure helps keep liquid molecules together. Lower the pressure far enough, and liquid can turn into vapor more easily. In a vacuum, exposed moisture does not need a flame to become unstable. Wet surfaces can bubble, evaporate, and cool at the same time. Now imagine the mouth, the eyes, the moist lining of the airway. The most exposed fluids are the first to reveal the problem. Saliva can begin to bubble. Tears can behave strangely. Moist tissue can lose water rapidly. But the bloodstream inside intact vessels is different. It is not simply open water in a cup. It is contained inside elastic tissue, under internal pressure, shielded by the body's structure. That is why the body does not burst apart, and it is also why the danger is more disturbing than a simple explosion. The cabin leak widens. The vapor jet becomes cleaner, sharper, tools drift toward the opening. Not because space is magically pulling them, but because air is escaping through the crack. Moving gas carries objects along with it. A tiny bolt spins into the white stream and vanishes. For the body, the first critical system is not the skin. It is the lungs. The lungs are delicate pressure organs. They are built for a world where air outside the body and air inside the body are not separated by a sudden extreme difference. In normal breathing, pressure changes are small. Air flows in and out because the chest changes volume, not because the lungs are fighting the vacuum of space in rapid pressure loss. Trapped gas becomes dangerous. Gas expands when surrounding pressure drops. That means air inside the lungs wants to expand outward. The body is not designed for that expansion to be held in place. If expanding gas cannot escape, lung tissue can be injured. The threat is not a cinematic full-body explosion. It is the failure of delicate internal surfaces that were never meant to carry that kind of pressure difference. This is why the quiet instruction of physics matters more than the loud image of science fiction. Pressure wants balance. If the outside pressure falls to near zero, any gas trapped inside the body tries to expand until it can match the new conditions. The lungs are the most visually understandable example, but gas can also expand in other spaces. The stomach and intestines contain gas. The middle ear depends on pressure balance. Sinuses are small air spaces hidden in the skull. A pressure change is not one event. It is a full-body negotiation, and the body loses that negotiation quickly. The red light flashes again, a pressure gauge drops. A hatch panel begins to slide. The spacecraft is trying to do what the body cannot do for itself: create a boundary. A spacecraft is a pressure container. It is not just a vehicle. It is a small artificial atmosphere, a machine that keeps invisible force around fragile biology. The body has lived its entire life under pressure. That pressure is easy to ignore because it is always there. At sea level, air presses against every surface. It pushes on skin, on the fluids in the body, on the lungs, on the water film across the eyes. The body is not fighting this pressure. It is built inside it. Remove it, and familiar fluids become unfamiliar. A droplet near the cracked wall grows cloudy with bubbles. Then it shrinks. That seems contradictory. It swells as vapor forms inside it, then loses mass as molecules escape from its surface. In vacuum, exposed water can bubble and evaporate. Evaporation carries heat away, so the surface can cool fast. That is where another movie myth appears. Instant freezing. A person exposed to vacuum would not immediately turn into a frozen statue. Space is cold in one sense, but vacuum is a poor conductor of heat because there is almost no matter there to carry heat away. On Earth, cold air and cold water can pull heat from the body through direct contact. In space vacuum, heat loss occurs mainly through radiation and through evaporation from exposed moisture. So, the body does not freeze in a single second, but exposed wet surfaces can cool rapidly as they evaporate. The nose, mouth, and airway surfaces can become cold. Droplets can freeze after losing heat. Metal near a leak may frost because escaping gas expands and cools. The cabin can show ice-like visuals, while the central danger remains pressure and oxygen, not instant freezing. No, the oxygen problem begins. In a normal breath, oxygen in the lungs crosses into the bloodstream because of pressure differences. The body depends on that transfer. In vacuum, the lungs are no longer a place where oxygen moves usefully into the blood. The surrounding pressure is missing. Gas exchange fails. Oxygen already in the blood is all the brain has for the next few moments. This is the true countdown, but not the kind movies like. There is no dramatic speech, no long struggle. The brain is extremely sensitive to oxygen loss. Without enough oxygen delivered by the blood, consciousness can vanish quickly. The body may still look intact. The face may not explode, the skin may not tear open, but awareness can shut down while the outside still looks almost calm. That is the frightening part. The most important failure is invisible. A transparent medical-style silhouette appears against the cabin window. Not a gore image, not horror, just a body-shaped outline with the lungs, bloodstream, and brain highlighted in soft light. The lungs dim first as useful gas exchange collapses. The oxygen in the blood falls. The brain glow fades. The danger is not that vacuum crushes the body. It is that vacuum removes the conditions the body needs to function. A human body is an earth pressure organism. Its chemistry is wet, warm, and pressure dependent. Its oxygen system assumes air pressure. Its fluids assume containment. Its lungs assume a narrow pressure range. Its brain assumes constant oxygen delivery. Vacuum attacks all of those assumptions at once. The cabin now becomes a demonstration of invisible physics. A sealed bottle floats near the crack. Inside it, trapped gas expands. The bottle bulges slightly. A flexible pouch swells. A drop of liquid inside a transparent tube begins to bubble. A suit glove hanging from a rack puffs outward as its internal pressure becomes obvious. That glove is a clue to what a spacesuit really is. A spacesuit is not simply warm clothing. It is not a jacket for space. It is a wearable pressure vessel, a life support machine shaped around a person. It must provide oxygen, hold pressure around the body, remove carbon dioxide, manage moisture, regulate temperature, and stay flexible enough for movement. It is a tiny spacecraft built in layers. That is why a suit looks bulky. Pressure has shape. If a suit were perfectly soft and inflated, it would become stiff like a balloon. If it were too rigid, the astronaut could not work. If the pressure were wrong, the body would not be protected. If oxygen flow failed, pressure alone would not save consciousness. If carbon dioxide removal failed, breathing oxygen would not be enough. The suit is not one solution. It is several solutions fighting each other. A close-up shows a suit arm flexing under internal pressure. The outer fabric expands slightly. Restraint layers hold it from ballooning too far. Joints rotate slowly, showing how difficult movement becomes when a garment is also an atmosphere. The suit must push inward enough to protect the body while allowing the person inside to bend. Pressure makes survival possible. Pressure also makes movement hard. This is one of the reasons spacewalks are engineering achievements before they are heroic images. The astronaut outside the spacecraft is not simply floating in a costume. The astronaut is inside a controlled environment that happens to be shaped like a body. Behind the visor are oxygen supply, pressure regulation, cooling, ventilation, carbon dioxide removal, communication, alarms, and backup systems. The vacuum outside is not dramatic, it is patient. If the suit holds pressure, space stays outside. If the suit loses pressure, space is suddenly inside the systems. The vacuum outside is not dramatic, it is patient. Red cabin sequence returns. The emergency hatch slides halfway shut. Vapor curls around it, droplets bend toward the narrowing gap. A pressure warning light pulses in silence. The spacecraft is trying to isolate the leak before the cabin becomes another piece of the outside. This is how protection works in space. Boundaries within boundaries. A spacecraft wall holds pressure for the cabin. A suit holds pressure for the body. A helmet holds breathable atmosphere around the head. Gloves hold pressure around hands. Seals hold pressure at every joint. The whole system is a chain of invisible containment. Break one link, and the environment rushes to equalize. Vacuum does not need to attack. It only waits for containment to fail. The next myth is swelling. Would the body swell in vacuum? Yes. Swelling can occur, but not like a cartoon body inflating until it bursts. When ambient pressure drops very low, water and tissues can form vapor bubbles in a process called ebulism. The body can expand because gases and vapor take up more volume than liquid. But skin and connective tissue are elastic and strong enough to limit that expansion. The result is dangerous swelling and disrupted circulation, not an instant explosion. A visual model shows a soft tissue layer under lower pressure. Tiny vapor bubbles form in the fluid spaces. The tissue expands, then resists. Elastic fibers hold the outline. Blood vessels remain contained but stressed. The image is unsettling because the body shape remains recognizable while the interior physics becomes abnormal. That is a recurring theme. Vacuum does not turn biology into a firework. It turns biology into a system operating outside its design range. The heart and circulation are also pressure dependent. Blood is pumped through vessels, and those vessels normally sit within a world pressing back on the body. In vacuum exposure, gas formation, oxygen loss, and pressure changes can disrupt circulation. The heart is not instantly crushed or burst. The threat is more layered, blood oxygen falls, tissues swell, vapor bubbles can interfere with normal function, and the nervous system loses the oxygen it needs. The brain has no patience for this. A few seconds of oxygen failure changes everything. The script must stay careful here. This is not a survival guide. It is not an experiment to imagine trying. Vacuum exposure is rapidly life-threatening. The exact outcome depends on conditions, duration, protection, and repressurization. But the safe conclusion is simple. The body needs pressure and oxygen, and space provides neither. A spacecraft cabin is shown before the leak. Everything looks ordinary. A water globe floats, a glove drifts, a tablet is strapped to a wall. There is no visible atmosphere because air is invisible. The scene feels safe because pressure has no color. Then the crack appears again. The invisible becomes visible only when it fails. White vapor, moving droplets, spinning tools, flashing alarms, a suit sleeve swelling hatch panels, sliding shut. These are the images pressure leaves behind when it disappears. This is why the best visual for vacuum is not a person exploding, it is a room losing its atmosphere. Body in that room is caught inside the same physics as the droplet and the glove, but with a more complex failure sequence. The droplet bubbles because water responds to pressure. The glove puffs because gas expands. The vapor jet forms because air rushes from high pressure to low pressure. The lung is threatened because gas expansion meets delicate tissue. The brain fades because oxygen delivery fails. Zone mechanism connects everything. Pressure difference. The black space outside the window is not pulling harder. The cabin is pushing outward. The air inside has pressure. The vacuum outside has almost none. Air flows from the place where molecules are crowded to the place where they are absent. The stronger the opening, the faster the pressure change. If the leak is small, systems may fight it. If the breach is large, the cabin can lose pressure rapidly. But even a small leak matters because pressure is not optional. It is the habitat. The phrase space vacuum can make people imagine emptiness as a force. But vacuum is not a substance. It is the absence of enough gas pressure. That absence becomes deadly because the human body is not empty. It contains gas, liquid, wet tissue, and chemistry tuned to an atmosphere. When the outside pressure falls, the inside begins to answer. A rotating visual shows 4 panels around a body silhouette. First, gas expansion in the lungs and other air spaces. Second, exposed moisture bubbling and evaporating. Third, oxygen loss and rapid incapacitation. Fourth, suit pressure preventing these failures. The panels move one by one, each linked by a glowing pressure gauge dropping towards zero. The gauge is the villain, not cold, not explosion, not space monsters. A number falling toward nothing. The movie version often chooses the wrong spectacle because explosion is easy to understand. But the real mechanism is more elegant and more frightening. The body remains visually human for far longer than the viewer expects, while the unseen systems that support consciousness fail almost immediately. A quiet body-shaped silhouette floats near a window. No gore, no bursting, no instant ice statue, just dimming lung glow, bubbling moisture at exposed surfaces, swelling tissue model, and a fading brain signal. The calmness makes it worse. The scene is not loud enough for what is happening. That is what pressure failure looks like. It is a catastrophe without a monster. Now the video shifts to the suit. A spacesuit stands in the airlock. The helmet visor reflects the black outside. The suit's life support backpack glows with status lights. A hose circulates cooling fluid. Oxygen flow moves through the helmet. Carbon dioxide is removed from the breathing loop. Moisture is controlled. Pressure layers hold shape. Everything the body cannot do in vacuum, the suit tries to do around it. The suit supplies a miniature atmosphere. It does not need to recreate Earth perfectly, but it must recreate enough of the important physics, enough pressure to prevent embolism, enough oxygen pressure to support breathing, enough removal of carbon dioxide to prevent poisoning, enough thermal management to prevent overheating or freezing of vulnerable systems, enough structure to keep that environment sealed. This makes the suit both protective and dangerous if it fails. Pressure alarm on the suit flashes. The outer layer swells slightly. A seam vibrates. A safety valve glints. The visual stays mechanical, not sensational. The message is clear. In space, the line between normal and lethal can be a seal, only millimeters wide. Inside the spacecraft, the emergency hatch finally closes. The vapor jet thins. Loose droplets drift away from the sealed panel. The red light continues, but the white blast is gone. Pressure begins to stabilize on one side of the hatch. The cabin is no longer one space. It has been divided into a damaged side and a protected side. That division is survival. Spaceflight engineering is the art of dividing danger from biology. Walls divide vacuum from cabin. Airlocks divide cabin from outside. Suits divide body from vacuum. Visors divide eyes from pressure loss. Gloves divide hands from boiling moisture and temperature extremes. Seals divide every joint from failure. Every boundary says the same thing. Keep pressure here, keep vacuum there. The body by itself cannot command that boundary. The camera moves through a clean airlock diagram: outer hatch, inner hatch, suit, oxygen line, pressure gauge, emergency seal. Each object is simple by itself. Together they form a pressure story. The human body is not protected by courage. It is protected by layers. This is also why the question, how long would someone last, is less useful than people think. The more important question is, which pressure system failed? How fast did it fail? What remained sealed? And how quickly was pressure restored? A slow cabin leak is different from explosive decompression. A suit leak is different from total exposure. A helmet problem is different from a glove problem. A brief accidental depressurization is different from extended exposure. The physics is continuous, not a single movie switch. But the central answer stays stable. Vacuum exposure is survivable only in extremely limited accidental windows with rapid restoration of pressure. And it is never safe. The body does not explode. The body does not instantly freeze. The body loses pressure protection, oxygen delivery, fluid stability, and normal gas behavior. That is more than enough. The final part returns to the opening cabin. The crack is sealed now. The red light fades to amber. A few droplets still drift in the air, smaller than before. One droplet contains a last tiny bubble that collapses as cabin pressure recovers. The suit glove settles back toward its normal shape. A tool stops spinning against a tether. Pressure has returned. And with it, ordinary reality. That may be the strangest lesson. The difference between a spacecraft cabin and lethal space is not always a wall you can feel. It is the invisible push of gas molecules. It is pressure held in place by engineering. It is the reason water stays liquid. Lungs exchange oxygen, suits keep shape, and the brain remains awake. Outside the window, space looks unchanged, black, silent, empty. But inside the cabin, everything depends on keeping a small pocket of pressure from becoming part of that emptiness. The movie version imagines the body exploding because that looks frightening. The real version is colder in another way. Space does not need to tear the body apart. It only removes the pressure that lets the body be alive.